I'm really grateful for this opportunity to share my work. Yeah, so my name is Sanjay. Thanks again to Ahmad for inviting me. I'm a PhD student at Berkeley, and this talk will be about how to build systems that perform visual reasoning when we only have access to a few labels for the task at hand. Natural language interfaces for visual media are one application of AI research that we're beginning to see more of. What do I mean by this? Well, let's look at some basic things that a person, which I've shown here, kind of like a cartoon person, might want to do with such an interface, which I've represented as this guy here, given this image on the right side. Just some basic things that they might want to do. So one thing is that they might want to find some object in the image, in this case, the man with the backpack. This might be useful if they want to crop that portion or draw a box around it or edit it in some way. And this is what we would expect the interface to identify as the object in this case. Like this localization operation, there are many atomic visual operations that we would want an interface like this to be capable of. And we want the system to be able to perform these operations across a wide range of images. For instance, in this image of a video game, if I gave the same command of find the man with backpack, we'd expect the system to output this bounding box, which again contains the man with the backpack, even though this is an image that has a lot of different qualities, properties than the previous one. We also want the interface to be able to handle multi-hop queries like this one. Is the man to the right of the donut, or to the right of a donut? Why is this multi-hop? Well, because this question is really asking two different things, which is there a donut? And then second, is the man to the right of the donut, if the donut exists? So the answer to the first part is yes, there is a donut. But the answer to the second part is no, because the man is actually to the left of the donut. And so the overall answer is no. And so in this example of these two different commands or queries, we've seen two key desiderata for a natural language interface for vision. First, that the atomic operations of the system should work well across different visual domains. And second, that we should be able to compose these atoms to perform more complex reasoning. Just to illustrate these goals in a broader context, let's consider different software applications where we might want to use a natural language interface. And we've begun to see this with Microsoft Copilot and with Adobe Firefly, tools that allow us to use language to control visual media in these applications. We might want to use an assistant like that to do video editing or to create slides like a PowerPoint or to create a flyer using some Adobe application. And each of these could involve a different visual domain. And we want our interface to adapt to all of these and to be able to adapt to a brand new application without much extra effort on our part. So this reinforces the first of the desiderata, which is that we want atoms that, these atomic operations that work well across visual domains. And another thing is that we might want to have workflows that involve multiple applications. And this could lead to some kind of multi-hop reasoning problem that's similar to the one that we saw earlier. So all of this discussion motivates the two goals that we'll focus on in this talk. First, we want to develop atomic visual operations that work well across visual domains. And second, we want to be able to do multi-hop visual reasoning by composing these atoms. And we want to be able to do all of this while not using much supervision, because if the system is presented with a new application or a new tool within an existing application, we want the system to quickly adapt. Okay, so the first part of the talk is about creating one particular visual atom in a zero-shot setting. And this was work published at ACL 2022. Let me first define the task that this atom aims to address. The task is called referring expression comprehension, which we will abbreviate as REC. And in this task, the model is given an image and an expression, so some text that refers to an object in the image. For instance, in this example, the expression is man with backpack, which we already saw before. Here we see that Uniter, which is a strong supervised approach for this task, selects the correct referent for this expression. But as we said before, this sort of a task is useful for many applications that could involve many kinds of images. And here again, we're looking at this image from a video game. And for practitioners that are dealing with some unique visual domain, like a video game or any other kind of niche visual domain, it would be useful to have a system for this task that works well without having to collect training data in the new domain. But, and also dealing with this shift in visual domain is challenging. So if I were to train a model on this domain and evaluate on this domain, which is what we're doing with Uniter, there are several different challenges that are involved. For example, the texture of this image is different. It's synthetic, whereas this one is a real photograph. Also, the sizes of the people in this image, you can see, are smaller than the sizes of the people in this image. And if that's true on average for images in this domain, that would also complicate the issue. And so if we look at what the Uniter model does for the same expression on this right-hand image, it chooses this person, which is not correct because this person is not the one with the backpack. So given these challenges with visual domain shift, we propose a baseline approach for this task in which we take the pre-trained model CLIP off the shelf and apply it to this task without any task-specific training. Our method, which we call ReCLIP, selects the correct referent in this example and in this one too. So these examples motivate this setting of zero-shot referring expression, which is where we perform this task without having to train specifically for it. And another motivation for this setting is that pre-trained models are becoming increasingly difficult to fine-tune, either because of their size or because they are made available only via some restrictive API. And because of this, it's useful to know how we can leverage pre-trained models for this task or for other tasks without fine-tuning. Okay, here's an overview of our method. Again, our method is called ReCLIP, and the input is an image. And we also take these associated object proposals as input, which I've shown here in these boxes, and an expression. And so the goal is to choose which of the boxes matches this expression best. For each proposal, we create an image in which that proposal is isolated. And we also pass the expression through a parser, which gives us noun chunks. Using CLIP, we score the isolated proposals with the noun chunks. So for each noun chunk, we get a distribution over proposals. We also extract spatial relations from the parser. And finally, the distributions for each noun chunk, as well as the spatial relations, are processed by a spatial relation resolver to obtain the final answer. In this talk, I'm mainly going to focus on this first part of the method, which is really the core, but the second part of the talk will have a flavor that's similar to this kind of multi-hop reasoning. Let's first look at a simpler expression than the one that we had on the previous slide, one that doesn't involve spatial relations. So let's just say that we want to find the gray cat. If we want to use CLIP to obtain a distribution over proposals for this piece of text, we need to figure out what inputs to give to CLIP. So in case you're not familiar with CLIP, it's a model that takes a set of images and a set of texts and outputs a score for each image-text pair that is supposed to represent how similar or how well the image matches the text. So given an image of a dog and two texts that say a photo of a dog and a photo of a cat, I would expect the image to have a higher score with the text that says a photo of a dog. So this is the format that CLIP expects, some set of images and some set of texts. For the moment, we won't do any parsing, and we'll use the full expression the full input expression as the input to CLIP. So in this case, that would be a photo of the gray cat. And as in the original CLIP paper, we're adding this prompt prefix here, a photo of. But the remaining question is, what images should I pass to CLIP so that the resulting scores will give me a distribution over the object proposals? And as I mentioned before, our solution for this is kind of very simple, which is that we create an image in which this proposal is isolated. And one way of isolating a proposal is to crop the image so that the result only contains that proposal, which you can see here. And this is the resulting distribution that we would get in this example. But there's other ways that you could isolate proposals. For example, here you can blur everything outside the proposal, and that's another way you can do isolation. And so in ReCLIP, we compute one set of scores by cropping and another set of scores by blurring, and we basically average the two distributions. So we sum the two sets of scores element-wise and then take the softmax. And you could view this as a visual analog of the text prompt ensembling that was used in CLIP's original paper. Okay, so we have this method that for scoring proposals, but there are other methods in the literature for doing this sort of thing. So let's see how this isolated proposal scoring compares with those. The first is called colorful prompt tuning, and this method transparently shades bounding boxes in different colors, and the text prompt includes the input expression followed by this mask token. And the way that this works is that this is usually used with a visually grounded masked language model to predict the color of the box by predicting what should go in this mask token. So in this case, we'd expect the masked language model to predict the color red, because that is the color of the box containing the desired entity. However, this method is not amenable to models like CLIP, which is not a masked language model, so we adapt it slightly by shading one bounding box at a time, and we pass to CLIP the text that is the input expression plus the words is in red color. The second zero-shot baseline that we compare with is GradCAM. You might be familiar with GradCAM. It's designed to provide a salience map to explain an image classifier's prediction, but it can also be used with models that output image text scores like CLIP. So if this was the expression, the man with his head down, we'd expect to get a heat map, or we would get a heat map that looks something like this. And in our case, we want to not only find one point or one subset of the desired region, we actually want to find the full region. So we want to get this box. And so we need a way to go from this heat map or from the salience map to one of the bounding boxes. The issue is that there might be more than one bounding box that overlaps the high salience areas. For example, in this image, there could be a bounding box like this one in red, but we would not want the red bounding box because it's really a bounding box that represents the bench here, or represents the group of people, and not just this one man. So because of this, it may not be enough to look only at which bounding boxes contain the maximum salience. We need to have some other way of choosing the correct bounding box. And what is done in prior work is to normalize the GradCAM score by the area of the GradCAM score of the bounding box by the area of the bounding box. So just divide by the area. And this area is raised to some power alpha just to kind of control the influence that this normalization has on the score for each bounding box. And this alpha is a hyperparameter. And so in our experiments, we tune it on the validation set of the data set that I'm about to show in just a moment. But keep this hyperparameter in mind, because as we talk about shifting from one visual domain to another, this hyperparameter will become important. Let's now look at results on this RefCocoG dataset. First, we have this random baseline, which randomly selects one of the bounding boxes. So there's not really any learning involved in this or any intelligent thing going on in this baseline. And with respect to this random baseline, the colorful prompt methods get a better accuracy. GradCAM, when used with CLIP, and after we tune this alpha hyperparameter on the validation set for this data set, performs substantially better. And isolated proposal scoring performs another 8% better than this. And of course, if we see that, if we look at a supervised method that's been trained on this data set, which I've shown here on the right side, obviously we don't perform as well as this because our method is a zero-shot method and this is a fully supervised method. But at least we can see that we've closed the gap significantly between these previous methods and the supervised method. But we said that we not only want to be able to do this task on the photo domain, which is the the data set on the previous slide is one example of that, but we want to be able to do this task on several different visual domains. So we also evaluated the performance of these methods on this video game data set, RefGTA. And on this data set, we did not retune the GradCAM hyperparameter. And you can see that the difference is very high, is much higher here than in the previous data set between the GradCAM and the isolated proposal scoring. And one explanation for this is that we did not retune this hyperparameter. So for example, if the video game data set tends to contain objects that are on average smaller than in the COCO domain, then the performance of the GradCAM method would be heavily influenced by the hyperparameter, which was tuned on the other domain. And this is the sort of sensitivity, the domain-specific sensitivity that we don't want to have when we're designing some atomic visual operation, like in this case, this object localization operation. And not only do we outperform GradCAM by a larger margin, but we see that if we take a model that is supervised on the COCO domain, and then we evaluate it on this other data set, so that's these two methods here, we outperform those methods as well with our zero-shot method. So in summary, when we put CLIP together with isolated proposal scoring, we're doing pretty well on this task. But there is an issue, which is that isolating proposals causes us to lose a lot of information, contextual information in the image. To see this, let's look at a more complex expression for this image, a black and white cat sleeping to the left of two other cats. The correct answer to this should be the green proposal on the far left, this one. But when we put this through isolated proposal scoring, this is what we get. The predicted answer is the pink proposal, which is to the far right. So this is an example that requires spatial reasoning, and isolated proposal scoring is not handling this well. There's like multiple different objects that are being mentioned, multiple different entities that are being mentioned in this caption, and answering correctly requires you to perform this spatial reasoning. Like this pink box would be correct if the expression were just two other cats, but in fact, we want to find a black and white cat that is to the left of those two other cats. And so this requires like multiple steps of reasoning, and this simple method of isolating proposals and scoring them with CLIP is not getting us the correct answer. So in order to figure out how to handle spatial relations, the basic question that we first need to ask is whether CLIP is useful for this kind of reasoning at all. And this will tell us whether we just need a different way of querying CLIP, or whether we need something aside from CLIP to do this spatial reasoning. For this analysis, we use Blender to generate synthetic images, and you might have seen images like this if you've looked at the Clever dataset. They are very similar. or they're really generated in the same way. So each image in this set contains two objects. And based on the colors and the shapes of the two objects in the image, and one of the relations between the objects, we generate two captions that differ only in the specified relation. In this example, the correct caption is a yellow cube is in front of a blue cube, and the incorrect caption is a yellow cube is behind a blue cube. And then CLIP's task is to determine the correct caption for the image. We're going to evaluate CLIP on this in a zero-shot fashion, so it's important that this is like somewhat similar to the pre-training class task for CLIP. Otherwise, it wouldn't really make sense to ask CLIP to do this in a zero-shot fashion. But note that this task is quite similar to CLIP's pre-training task, except that we're ensuring that spatial reasoning is required to answer correctly. Another sanity check that we do is to include this control task, which is very similar, except that we don't include spatial information in the captions, and instead the captions just differ in the attributes of one of the objects. So in this example, we might have a blue cube and a yellow cube would be the correct caption, and an incorrect caption could be a blue cube and a yellow sphere. The difference between CLIP's performance on this version of the task and the spatial reasoning version would tell us whether CLIP accounts for spatial relations in the image text scores that it outputs. This plot shows the performance on the synthetic tasks. The labels on the x-axis are different versions of CLIP, so we've evaluated a bunch of different CLIP versions, and the y-axis represents accuracy. So first, let's look at the non-spatial version of the task, which is the green bars. And on this version of the task, the models score about 90% or higher across the board, across all of the versions. So clearly, the models are able to operate well on this domain of images, and they can perform this task well when there's no spatial reasoning involved. But the accuracy on the spatial task, which is shown by the blue bars, is only around random chance. And this indicates that a model like CLIP, which is trained only on image caption pairs, may be unlikely, and certainly in the case of these models, it is unlikely to help us handle spatial reasoning. And this observation extends beyond just the referring expression task. And indeed, there have been a bunch of other papers since we submitted this one that have also made similar observations about CLIP's ability to handle spatial relations. Okay, so this basically brings us to the end of the first part of the talk, and we have two main takeaways. First, for the task of referring expression comprehension, we've seen that ReCLIP, and specifically the isolated proposal scoring method, is a strong baseline for zero-shot referring expression comprehension. And second, we've seen that CLIP's spatial reasoning performance is quite poor. Going back to the goals that we set at the start of the talk, what we've talked about so far in the case of this particular task of localizing an object, which is called referring expression comprehension, we've talked about how to create a visual atom for this task that works across different visual domains without needing any retraining. The next part is going to be about the second goal that we talked about at the beginning, which is how to do visual reasoning that combines multiple such atoms. And one reason why this is a key challenge is that we've already pointed out that some pre-trained model like CLIP can struggle with this kind of reasoning, particularly in the case of spatial reasoning. But there can be other such types of reasoning that are difficult also. Okay, so this is the second part of the talk, and I'll talk about how we can use code generation to orchestrate reasoning across different visual atoms in the context of visual question answering. And this was a paper published at ACL 2023. Okay, Let's start with the task definition, since this is a different task than what we were just talking about before. Visual question answering is the task of answering a question about some image, or it could be a set of images. So consider this simple example. Is there a donut? Recent work in zero-shot and few-shot VQA has provided methods that perform quite well, especially on simple questions like this one. For instance, few-shot PNP VQA is a system that generates captions for the image and feeds them to a language model along with in-context examples to answer the question. So the system answers yes here, which is correct. But now let's consider a more complex example, which we talked about earlier in the talk. Is the man to the right of a donut? And this example is more complex because it asks the system to both determine the existence of the donut, which is here, and to reason about the spatial relationship between the man and the donut. In this case, few-shot PNP VQA answers yes, which is incorrect, because the man is in fact to the left of the donut. In this paper, we tackle the problem of answering more complex questions like these, like this one, in a few-shot manner. And this is our method, CodeVQA. And it's at high level, it's a framework for doing VQA in a modular fashion by using code as the intermediate representation. So in the first phase, we use a large language model to generate a program based on the question. This program references visual primitives, which are defined based on off-the-shelf vision models. In this example, the program invokes a simple VQA function called query here, and an object localization function called getPause. Having generated this program, we execute it by calling these functions on the image. This simple VQA function is able to correctly answer this simple question, is there a donut, as we've already seen. And the answer to that triggers the if block. And then there's also an object localization component. So first, this function is used to find the position of the man, and later it's used to find the position of the donut. And then these two positions are compared to produce the correct answer. So in this case, we find that the x-coordinate of the man is actually less than the x-coordinate of the donut. So this if statement does not proceed. And so the answer is no. So that was one fairly straightforward example, right, involving spatial reasoning. But CodeVQA can also help us handle even more complex situations, such as if we have a set of input images, even though the visual atoms, these functions themselves, were not necessarily trained on sets of images. So let's consider this question now. Is it true that there are 4 pandas? Few-shot PNP VQA, if we were to prompt the language model with captions for both of these images, once again answers incorrectly in this case. It says, no, there's not 4 pandas, but in fact, there are. On the other hand, CodeVQA generates a program that breaks this question down into operations on each individual image. So what it does is this program has this for loop that goes over the images, and for each image, it counts the pandas using this query, and it compares the result. It adds these counts together across the images, and then it checks whether the result is equal to the number 4, since that's what was mentioned in the question, and produces the correct answer by doing this. Notice that in this example, we only use one visual atom, or one visual function, which is query. But by combining multiple calls to this function, along with Python logic and arithmetic, CodeVQA produces the correct answer, while the baseline does not. Okay, so now I'll do a slightly deeper dive into some of the details of the method. So in the first phase, we saw that CodeVQA generates a Python program by prompting a language model with few-shot examples. So this is one such example that we might feed to the language model. And whenever we're doing prompting for a language model using in-context examples, one important question is how to choose the set of in-context examples for a given question or input. And the way that we do it in our method is by computing sentence embeddings of the question that is given as input and of all of the questions in our set of annotated programs. And then we retrieve the questions and programs where the sentence embeddings are closest to the embedding of the new question that we want to answer. The second phase of CodeVQA involves executing the program by calling the visual functions. Also, we can call them visual primitives. So I'll just give a description of each of these. First, we have this query function, which we've already seen. It's exactly the same as the few-shot PNP-VQA method I described earlier. So what this does is generate captions for the image and provides the captions and the question to a language model to generate the answer. There's also a getPause function. In our case, we do this by GradCAM. Now, you might be wondering why we use GradCAM and not something else, since we said GradCAM has issues in the first portion of the talk. But the key is that in this case, we don't need a bounding box for the object. We just need one point if we want to use this function for spatial relations. And you might remember that the key issue in the first part of the talk was the key issue with GradCAM was going from this point to like a bounding box for the whole object. So since we don't have to worry about that with spatial relations, we're just going to use GradCAM and make things simple. So we take the image and the referring expression and generate a GradCAM map, and then take the argmax of that GradCAM map, and that gives us the XY position of this object. And the last visual function is used specifically in cases where we have multiple images in the input. And this is used to select which is the image that best matches this image description. So for example, if I was given this set of images and the referring expression said the lemons on a white plate, or the lemon on a white plate, this would be the only image that matches this description, and so we would expect to get that as output. One important thing is that while in our paper we mainly consider these visual primitives, it is for a practitioner who has a new function that they want to incorporate into the system, it's fairly straightforward to do this because all you need to do is modify the set of in-context examples to use that function in the appropriate way. And then, you enable the language model to generate that function. Okay, so let's look at some quantitative results. We evaluated our method on several data sets in the paper. I'll show results on a couple of those data sets here. First, there's the GQA data set, which has questions about single images, often involving spatial reasoning. And CodeVQA outperforms the few-shot baseline here. And it's also on par with these other methods, which are concurrent with our work that also propose code generation methods. But I think a more exciting improvement is on the cover data set, which is a data set of questions about sets of images. So we saw one example earlier with the counting of pandas, and there's a lot of different reasoning that you can do about sets of images. The other methods that I showed on the previous slide don't present results on this data set, but we do outperform the primary, this few-shot PNP VQA baseline by a large margin here. And we saw in the earlier example that one reason CodeVQA can help is by obtaining some necessary information, for example, spatial information. But let's look at this other example and see if that's the only reason why CodeVQA helps or if there's something else. So here we see an example from Cover, where the baseline does generate captions that have the necessary information. So this question is about whether the two trains are the same color or not. And the few-shot PNP-VQA generates these captions for the two images, and the captions do have the correct colors here. So yellow and red. But still, the language model answers this question incorrectly, saying that the two trains have the same color. On the other hand, CodeVQA gets the color for each of the trains and then explicitly checks whether these two colors are equal. And so because of this, it correctly answers no to this question. So it's not that CodeVQA only helps for retrieving useful information. Even if you have useful information in the captions, it can still be useful to generate this program to do this reasoning over the information, rather than just to provide the language model with all of the information and expect the language model to reason correctly. Our paper has several different types of analysis. I'll go over a couple of them here. I think one of the interesting ones is about how the results change as the number of input images changes in the Cohere dataset. So as I said, Cohere has questions about sets of images, and these sets can have different numbers of images. So there's some set of questions that have only one image and some set that have 5 images. And the interesting trend here is that overall, the improvement from CodeVQA is greater when there are more input images. So when there's only 2 input images, the improvement is less than 2%, but when there's 5 input images, the improvement is more than 6%. You might notice that CodeVQA has lower accuracy in this category, but it's worth noting that there's only 12 such examples in this column, but there's like hundreds or thousands of examples in each of these 4 columns. So I think there are limitations of our method, but I don't think this is really reflective of them necessarily. We also tried to understand how important the in-context example selection is. So I mentioned earlier that in the first phase of the method, we do in-context example selection using sentence embeddings for the questions. And we compared this with doing random retrieval of examples instead. And we found that CodeVQA, the improvement from CodeVQA over the baseline is much larger when examples are retrieved using embeddings rather than when they're retrieved in a random fashion. Okay, so there are many cases where our method works well, but it also, of course, has some limitations. And one of them is that adding modules can sometimes decrease the net performance. So I'll give an example here, and we also have a more detailed study in the paper. So this example is taken from the OKVQA dataset, which focuses on visual questions that involve external knowledge. So to deal with some questions like these, we added a knowledge query module to CodeVQA that works by querying a language model for some question about general knowledge. This question that I've shown here is a person who eats only these is called what? And the image is showing some fruits and vegetables. And so the idea is that this is a person that only eats fruits and vegetables, like a vegetarian, basically. And the few-shot PNP-VQA baseline, which generates captions and presents them to a language model to get the answer, answers vegetarian, which would be a correct answer. But CodeVQA generates this program where it first asks what is on the plate, and the answer produced for that question is strawberry. And this is fed to the language model, which answers strawberryan, which is not quite correct, obviously, because it's missing all of the other stuff that is shown in this photo. So this is an example where a suboptimal initial step, or maybe a suboptimal response to the initial step, can kind of propagate through the rest of the reasoning process and lead to an incorrect answer in the end. So this is one challenge with adding modules. There's also other challenges, like, maybe if you add some new module that gets used in cases where you don't want it to be used, and maybe you were already answering those cases correctly before. So that can also decrease performance. So I think all of this is very interesting and needs more exploration if we want to push this direction further. I also wanted to mention that we've been talking in this code generation portion about VQA, but I wanted to bring it back briefly to the referring expression task that we looked at in the first part of the talk, because you could imagine using some program synthesis sort of method for doing that task as well. We didn't evaluate this in our work, but a concurrent paper called Viper GPT does use a similar program synthesis approach for referring expressions and shows that it results in higher performance than ReCLIP in a few-shot setting. So the takeaways for the second portion of the talk are that program synthesis improves few-shot visual reasoning, and that if you have more visual inputs, this could lead to a greater improvement from program synthesis. And finally, that selecting relevant in-context examples matters. And of course, there's limitations for this approach, and I think there's a lot of exciting future work that can be done on pushing this program synthesis sort of approach to visual reasoning further. And aside from that, I just wanted to thank you all and give credit to my collaborators, without whom this work would not have been possible. Yeah, happy to chat more about all of this or answer questions. Okay, thanks for the question. The question is, how are you extracting bounding boxes for questions in isolated proposal scoring? The question is about extracting these proposals for isolated proposal scoring. And we used proposals that were provided by a previous work, at least for the COCO datasets, which the previous work is called MapNet, and I think they used faster RCNN to get the bounding boxes. So faster RCNN trained on either Visual Genome or COCO to provide the bounding boxes, I believe. Just to confirm, it was mask RCNN that was used to produce those boxes, I believe. Okay. Ahmad has another question. If we look at CLIP pre-training objectives, how can spatial reasoning be made a part of it? If I remember correctly, it maximizes the image with the relevant text pair. Should it be part of the data set? Yeah, I think this is a really good question. And I think there are some papers over the last year that are exploring this more, how to make something like spatial reasoning or other kinds of reasoning part of the CLIP pre-training objective. I think like you said, it could be made part of the data set by constructing image text pairs where you need spatial reasoning to correctly answer, to correctly select the right text for the given image. Like the synthetic test that we talked about, where we had these images with two objects, and we have to select a yellow cube is in front of a blue cube instead of a yellow cube is behind a blue cube. If there's a way to do this in a more general, for more general images, I think that would that could help for improving the spatial reasoning performance of CLIP. But I think even if we cannot make CLIP do spatial reasoning well, it's okay, because we have this this code generation approach that allows us to handle that sort of stuff, those multi-step reasoning sort of things, and we can use CLIP just for trying to associate attributes and nouns with the correct images or parts of the image. Another question, what language are you using for code generation? The language model we used is Codex, Code DaVinci 2 on the OpenAI API, which at this point I think is only available via request to OpenAI. But I think that a similar approach can be used with like some of the other GPT variants. I think it would be really cool to make this work with open source code generation models. And I think the open source models are getting much better these days, like Wizard LM, for example, and StarCoder. So hopefully it'll be possible very soon to do this with an open source language model. Okay, great. Thanks for having me, and sorry that I wasn't able to hear what you were saying over the audio, but yeah, thanks a lot for having me. Feel free if you have questions later to send me an email.